Hello guys and dolls, welcome back to Honey Badger 3D Print and Paint. Today we're at Laserlines looking at the Stratasys J55 and I got that right on the first time, so well done me. Talk to me about what this is, because it looks like a very high-speed microwave and I suspect that it isn't. So, so talk to me about what it actually does and why this is really actually quite exciting.
So this is part of the PolyJet range of 3D printers, and the way it works is instead of jetting ink on paper, it jets photocurable resin on a platform, layer on layer, forming a 3D printing object. So you've got a multitude of colors, you've got different cartridges that you can see here. Full CMYK, it's Pantone validated. It can also do flexible materials. It can do also clear materials. So every time materials combine, it can give you a different color. So for example, black and white combines, it gives you different shades of gray.
So let's be clear, that's significantly different to anything else on the market right now.
Yes.
The fact that it's Pantone
Validated
means that you can actually map the correct colours for your brand. So for those who don't necessarily know, when you work in marketing, you have very, very specific colours that you own and that are your brand and are your colours. There is a colour called EasyJet Orange for EasyJet, and they don't use any other colours other than that. So the fact that you can map those colours so accurately is completely different to anything else. Everything else at the moment is kind of an approximation of colours, and it kind of mixes other bits and pieces together, and it kind of gives you a brown, but there's no real gradation in it. It's just sort of kind of a washy out brown. But this isn't that. This is full colour.
Pantone validated. So if you pick your Pantone code, you can select certain areas of your part, and that Pantone code would make sure that it's printed on the part. If you want before that, you can also print it as a sample, check it, make sure it's the right color for you, make sure it does it, but because it's Pantone validated, that step is not necessary.
So that's really cool, straight out of the gate. So why does it spin?
So normally with this type of technology, and that's what we do also with the higher end range, you've got a static platform and a moving head.
Yes.
With this technology, it's still PolyJet, but you've got a moving platform and a static head. And what that helps with is also with the space and maintenance.
Right.
So normally when you have a moving head, you need a stationary area where the head would go back into position, back into position, back into position. With this, you don't need that. So when you have that, it increases the size of the printer, you need a cabinet next to it and so on. But this is really quite a space-saving machine, giving you quite a lot of area of printing.
Because, I mean, we're getting dangerously close here to being a desktop printer. I appreciate we've got the cupboard underneath and that contains all the material in it, but we're not talking about sort of the F370, which is in and of itself a huge cabinet on its own, or other industrial grade machines that take up a huge amount of real estate whilst doing something intensely complicated. This is doing something intensely complicated whilst spinning in a small space.
Correct. The version down from this is the J35, and that is a bench top. So that is from here to here, and you have all the materials down at the bottom. But that only does 3 materials, so you're very limited in terms of how many materials you can print at once. But otherwise, it still does multi-material, so you can print full part, rigid part with a flexible part with transparent part on it. So I always say with this technology, the more open your mind is, the more you can do with it.
It's really cool. I mean, apart from the fact that it's been put in a relatively beautiful package anyway, let's talk about price, because I think that is important, and we have to bear in mind that this isn't obviously what everybody goes out and buys, right? This is how much for the whole stack?
This once the part is finished, you remove it from the platform. The support material is like a jelly type support material that you just wash away. So I always say as a full package, you're looking at approximately 90k.
It's not, I mean,
worst case scenario,
when we're still talking about full colour,
Correct.
relatively minimal post-processing, I mean, it's printing at a fair pace. Like, this isn't slow. It's spinning very quickly, which I assume it's A, supposed to do, and B, is a very impressive thing. 90K in a commercial setting when you're talking about return on investment isn't a particularly complicated business case to make when you consider that traditional polyjet is like 250K before you then get into the everything else out the back of it. And it's just really
and that's
cool.
why this was released. So it goes into, it's an office-friendly printer. You can put it into a design office, into an industrial design office, universities, and so on and so forth. So it's great space saving compared to the bigger polyjet printers, which they still have a space in the market. We still see a lot of companies interested in that technology. Plus, you can print on that technology. You can print on fabric. So we've got a 3D printed dress there that you can take a look at. So yes.
Take a look at that in a minute. All right, okay, well thank you very much for showing it. It's very exciting technology and I can't wait to play about with it a little bit more. But let's catch you on the next video and we'll do some quick overshots of what else is available and what this has managed to produce out of this system. Maintenance worker for local councils, and Carl's just drives around on that all day, really, pretty much. He's a cripple, professional cripple. Try to showcase new tech on the market. We try to do different things. Going to Form Next again this year.
Yeah, we're there.
Yeah, I love
We're there with
like
Stratasys.
it's
Factory. How buzzing is that?
yeah.
It's like buzzing and like I was there this morning.
Problem is Form Next is packed. Like Form Next has got what 870 exhibitors last year. This place is 79, and it's like, oh, okay, cool. Yeah, it's around the corner somewhere. One of them is HelloFresh. You're like, oh, okay, cool. Yeah, we do this. So we sort of.
Stratasys have developed an augmented reality app which can be downloaded from the App Store straight onto your phone to be able to visualize the printer into your offices. Press the clamp and remove the material out, and then to put it back in, you just slide it in and there it's back in place. What you can also do on the printer is print with VeroClear, which is a very good material if you have the requirement to print any transparent parts or any glass simulating type parts.
Hello guys and dolls, welcome back to Honey Badger 3D Print and Paint. Today we are with the University of Liverpool with the Scaffold project and Lupo, and you are going to tell me what this crazy thing actually does.
Okay, so basically, if you think 3D printers, all 3D printers are basically boxes where you make objects inside the box. Our goal with this project is to create a 3D printing device, a 3D printing system that can remove any build volume limitations. And we are going to do that by having the robot being able to climb on the object as it's printing it. So that way you can reach any nook and cranny of the object that you might need to print, no matter how big it is, because as the object get bigger, you just climb along and you keep printing. So the way we are doing it at the moment, also the name of the project is Scaffold, because we are using scaffolding geometry that lets the robot both locate itself on the part so that you know exactly where you are and you can keep printing with some accuracy, as well as move. Basically, you see here there are 2 sets of holes for each color. The robot is equipped with 2 grippers, one on the arm at the back here, and one on the base that it's covered now because it's latched in onto the frame. But basically, when it reaches the limit of its build area, it takes the printer on the arm, so it turns all the way around, reaches the top one, detaches the bottom, the one at the base, pulls itself up, and latches again. I think they're going to have a video. Oh, actually, it's showing on the screen right there, right now.
We'll put a video of it actually doing its thing.
Yeah.
But we're effectively talking about in this particular configuration at this stage, we're effectively talking about infinite Z, where the robot has a finite Z inside of the lead screw.
Yeah.
As the project continues to print, it prints more of these boxes, which are on the back of whatever it's printing, and it is continuously moving up the Z-axis by moving in and up and in and up, and it is continuously moving itself up the back of the print as well. So in this configuration, you've effectively got an infinite Z. But to be clear, that's not the limitation, not the end goal, right? This is just stage 1.
So basically, we started working on this project earlier this January, and so it's now June. We've basically had like 4.5 months, 5 months to develop this, and this is just a proof of concept, just so that if I tell you we have made a 3D printer that can climb, you're not just gonna laugh at it and it's like, oh, what is this? Like, is this a joke? No, it actually 3D prints and climb, and this is all this is. This was developed very, very quickly. It was mostly a matter of getting it to work, not getting it to work nicely. So that was the entire.
So we can forgive a little bit of the lack of beauty.
No, you can see like the layer lines. You can see all the ringing. You can see all.
It's the first iteration, right? And there's a reality. This is just a proof of concept to show that in theory this is how this can potentially work.
Oh, absolutely.
So talk to me about applications, right? Because it's all well and good saying we've got an infinite Z, and then we expand that by going got an infinite X and an infinite Y. But what are the actual practical applications once you get to a final stage?
Okay, once we get to a final stage, this would be after years and years of research, most likely. The final application would probably be construction. So if you imagine building a house, you could have a lot of these robots working together cooperatively to build both the structural components, the insulation, to build all the parts of the house. But something that might be able to be done a bit earlier is if you need to make tooling for manufacturing of large composites, so large molds that you then lay carbon fiber or glass fiber on, and then you you put the epoxy on.
Yep.
Yeah. So
hold on. So
yeah.
So in the first instance, we're talking about a robot that is effectively capable of moving independently to build multiple shafts.
Oh yeah.
Then we're talking about the next layer of that, which is working with swarm mechanics to mean that multiple machines building.
Yeah, exactly.
Then inside of that, we're talking about multi-material swarm robots.
Yes.
That are able to perform separate tasks, but all contribute towards the same whole.
Yeah, and if we want to keep going down the rabbit hole as well, because you have a path of the scaffold geometry embedded on the part, you could create parts that have paths for these robots to carry out maintenance as you go ahead. So it's not what you could also use it further down the line, not purely for the manufacturing, but for running other tasks. Kind of like you could have your building with the pneumatic air tubes to carry messages. Imagine it that it's just a robotic caterpillar that crawls in the wall. Obviously not very practical, but I couldn't think of anything else. But yeah, so no, there is a lot of work that needs to be done. And if you will be able to, if you ever see an evolution of this system, I say hopefully, because we are looking for partners, we are looking to expand the research group. But yeah, so if you ever see a new iteration of this, it will look completely different.
I mean, this in and of itself is a contextually complicated design, right? Because we've got a cantilevered X, if you want to call it that. We've got a rotational Y, I suppose.
It's like, I call it alpha. Alpha for the angle, radius, and then Z.
Right,
Yeah,
so
sorry.
Z is contextually traditional.
Yeah.
About this is although it's a reverse C because your C's at the top rather than the bottom. And then you've got, I mean, the way this is work, the kinematics of this is, I guess it's kind of similar in a core XY, but it isn't because the A and B are still, or the radial and the axial are still independent of each other.
Yeah, like
They just have to, both of them move to produce a single linear motion.
yeah, but it's like the best way to explain it. I might be using some complicated words, so please stop me if it gets too bad. But most machines that you use a Cartesian motion system, which means that you have 3 linear axes, all perpendicular to one another, which then means X gives you X, Y gives you Y, and Z gives you Y, Z gives you Z movement. But with this one, we are using polar kinematics, which then means we are using a polar coordinate system, which it's defined by a point, its origin, an angle, and a length of a radius. Right. So this is the the kinematic system that we are using. That's the reference system that we are using. But
so that's intensely complicated, right? Because
you just you have an angle, you do cosine and sine law, and the radius. It's trick. It looks complicated, but out of all the various kinematics that you find supported by Clipper, is actually not one of the worst.
Yeah.
Or like the one supported by the Rep platform, where there is one that is I think a Homer printer that is all the weird linkages, you can get a picture of it probably.
Yeah, but no, the articulated arm piece.
Yeah.
If anything, I mean, once it's done, it'll work more like a 5-axis radial CNC machine. In reverse, because it's not subtractive engineering, it's additive, right? Because it's moving. Because one would imagine it would have to move if it's doing multiple materials in multiple places horizontal. Then the tool head would have to be axial as well, and then even to be able to
I wouldn't think of it necessarily as a CNC machine. It would look a bit more like industrial robot arm.
Right.
So if you think 6 degree of freedom robot arm, you just take off 1 degree of freedom, and you still have something that looks exactly the same, but it will work for our application as well. We don't really need the extra degree of freedom because the final degree of freedom would be to control the rotation. I'm not sure which one it is, if roll, pitch, or yaw. For the tool head itself, but it's not strictly necessary because we don't care about it yet. But so there is a lot of the I can talk for a long time about a lot of the technicalities of the project, all the various challenges, why we decided to select the components that we use. To be honest, for the selection, it can be shortened to, we only had 6 months to get something working, and we tried to get it done even earlier to show it at the show today.
So have you got papers published on this already?
I am writing the papers at the moment. I just have to take a little bit of a break because I need to go back to write my PhD thesis, which is in a completely different field.
Especially when you built this in January, it feels like your PhD you'll just write in a weekend and just... Okay, thank you very much for the time. It's a very, very interesting project. We'll put links to the video description and things like that, and when the paper's published, we'll put a link to that as well. Thank you very much for the time. Thank you very much for showing us. Catch you on the next one. Hello guys, dolls. Welcome back to Honey Badger 3D Print and Paint. Today we are at FYOUS booth, or FYOUS, depending on how you want to pronounce it. And you are doing reusable mold technology. So talk to me a little bit about what it is you're doing and why it's special.
So this is the world's first. It's the world's first high-resolution automated pin tool. So you remember that kid's toy, the pin art, you put your face and your handprint? It's a very expensive, advanced version of that. So we can configure the pin heights very accurately, and they can take a tremendous amount of pressure, and we can make forms, create molds that can be used for vacuum forming, PU casting, carbon layout, and the mold is completely reusable. So within minutes, we can reconfigure it or shapeshift it to a new mold and then use it again.
So one of the biggest issues in molds is their lifespan, right? It's how long you can use it for before eventually you just have to throw it away and make another one. You have master molds and everything else. And you're saying that you've effectively eliminated that from the workflow completely, because apart from the fact that I'm assuming these are relatively hard wearing, they're also easy to configure going forwards to mean that you can just completely retool your workflow in a matter of hours, in a matter of minutes, rather than the complex process of creating master molds where you have to do Boolean adjustments and everything else.
And you can go straight into production as well, right? So once you kind of done all your prototyping, your little iterations, that tool can be used for thousands of parts straight away.
So it gives you the flexibility to do low yield runs, I suppose. So generally speaking, when you're doing molded parts, you have to do relatively high production runs to offset the cost of making the master molds and retooling everything and getting everything set up. So you have to make 10,000 of whatever it is you're making. But you've created a way for you to be able to do really low volume without having that cost associated and that tooling time that has to be built into manufacturing flow. So what kind of industries are you using this in at the moment?
So we've just done a load of samples recently to demonstrate the application. So we've got a little RC car cover going around like that. So we've done carbon fiber parts. So can I just get some?
Yeah.
So for example, this is a vacuum formed RC car cover.
Right.
So to 3D print something like that would take 7 to 14 hours. And usually you wouldn't create a mold because you'd have the mold waste. You need a massive CNC machine. But with polymorphic molding, don't need any of that and there's zero waste.
Yep.
Can do carbon layup. So that's a bike seat. Try and bend that.
Oh, that is proper carbon fiber, actually. Yeah, fair play.
So we made that mold in 20 minutes. And then we use the same mold to create this foam part.
So the types of applications of this, we're talking about, I mean, at a base level, something like being in a Foot Locker and being able to get custom inserts made in a vacuum former in store that perfectly fit you, that require no real professional, I say professional level, you know what I mean? Like they don't require a specialist to come in to have to figure out the exact contours of a person's foot. They could literally just make the mold, put it into their machine, put it into their former, and off they go.
Well, you do a 3D scan of it and it sends it to us and then the mold automatically configures.
Mold automatically configures?
Yeah, you just stand it or impression it. It's mechanical. Right, so
okay. So whoa. So it's you plug in what like a type CAD model, and then it configures itself to it.
Yeah, so you just send us CAD data and we put it into our software. It's like almost like a slicer, I guess. And then all the pins will move.
Right. So, yeah, light bulb. So originally what this looks like is the pin models, right? Where you press something onto it and then you have a mold and it stays like that and then you're able to go and do it. But it's not that because you're taking a digital 3-dimensional model that is then that the pins are then adjusting to in real time to then create the mold there. Oh, that's much cooler.
So, like, yeah, you don't need to be with us. You just send us CAD data. Really, it just automatically does it.
Yeah, that's a lot cooler.
That's interesting that it doesn't come across. I need to change my bit.
I mean, initially, I genuinely thought when you said it's like the pin thing. I was like, oh well, yeah. So you just take this and you press it in, and then that's your master, and now you've got a thingy. But no, it's actually
zero waste. So you create that mold. You didn't need anything to create digital information.
Wow. Okay. Cool. All right. That's pretty cool. That's why it's cool. That's pretty cool.
Yeah, you see here, like this is just a CAD model.
So he's taken the 3D scan of his face. You're then able to create the mold directly from that, which is and then creates the master, and then you're just able to mold straight from there. Okay, that's pretty cool. All right, fair enough. Thanks very much for the time. Catch you on the next one.